Alright, this is basically proof by construction. This is assignment A2Q2 for reference. We are proving that, what are we proving? Right, so for any n greater or equal to 3, show any 2-edge coloring Kn has either monochromatic Hem cycle, or Hem cycle consists of 2 monochromatic paths. Basically, I'm viewing only like one colored Hem cycle as a special case. Of the second one, basically it's still 2 paths, except one path is empty, and that is fine. So this is a proof by construction. I will just run through the algorithm, prove it works, at least to me. So let's say V1, V2 are just 2 arbitrary vertices in Kn. They are not equal. We have some notation. Pi is a path that is either 2 union of 2 monochromatic path. I cannot speak math. Or chromatic. Basically, one of the 2 paths is empty. P1, we start with vertex, like one vertex. P2 is P1 and some other vertex because it's Kn. Every vertices are neighbors to each other. So yeah. So path is represented by the vertex we are choosing. CVI plus 1 is the color of the edge, VI plus 1. Given Pi is defined, because we are building the path iteratively, to find Vi plus 1, we need to like define Pi first, and then be like, oh, which vertex is next? And it's 1 in some unvisited vertex, so all of the vertices, except those ones that's already in Pi, and given Pi is defined. Okay. Now we have like, this is the base case, I guess. This is the hypothesis that we have Pi, and now we are choosing Vi plus 1, or well, we are picking any Vi plus 1 that's not here, and construct Pi plus 1, which is the next path in the iteration. So there are a few cases. One is Pi itself, the path is monochromatic. Then if C1, so the start of the color equals to the end of the color, because we know it's either the union of 2 monochromatic paths or simply one color. If the start equals to the end of the path so far, means that there's only one color, right? We can just attach Vi plus 1 at the end. You can also do it at the start, but it doesn't matter. If it's a different color, now we have a union of 2 monochromatic paths with the other color. I will just say color 1, color 2. So color 1. And we don't know about Vi plus 1. It can be color 1, it can be color 2, but if it's color 2, we have 2 union of 2 one colored path. If it's color 1, it's still monochromatic, and it's fine either way. Okay. But if Pi itself is not monochromatic, so this is like if, I guess, this is else, then we need to discuss by cases to see whether do I need the right hand side? I don't think I need the right hand side. Well, I'll bring it back if I need it later. Yeah, so we need to discuss by cases where to like attach Vi plus 1. I just realized my typo. I was using typist and my mind is telling me latex, so that's, yeah, some with notation. So the order will be, we attach it at the back if that holds. So basically we have something color 1 first, from V1 to some V, let's say VK, somewhere in the middle, and from VK to VI, I'm writing 1 here, but like I'm kind of simplifying it, to VI. This is color 2. So this is case 2. We don't have a monochromatic PI so far. The PI looks like this. Alright. So when do we attach it to the back? If the color between VI to VI plus 1 is equal to, I'm just gonna be like that. So we have VI plus 1, the previous one, some dot in between, and we have V1, V2, some dot in between till VK, that's the same color. This would be V2. Okay. So yeah, if VI plus 1 is the same color as VI minus 1 VI, we can just attach, I need a different color. We can just attach VI plus 1 at the end, right? PI plus 1 will still be a union of 2 color. And sometimes we attach it to the front, that is when V1 VI plus 1. So VI plus 1 can be attached to the front when it's the neighbor of V1, and the, this is case 1. I'm gonna copy this to drop case 2. No, you do not belong here. So we add VI plus 1, attach it to the front when VI plus 1 to V1 is the same color as V1, V2. So now we are still a union of 2 monochromatic paths. Okay. Move V1 from front to end and then attach VI plus 1 to the back when VI plus 1 V1, which is still this path, is not equal to this one or this one, but it's equal to color of V1 to VI. So well, this is the original path, right? But let me see. Let me see if this is necessary, because I feel like this will capture all the cases now that I look back on it. But let me have a look. So I'm saying is VI plus 1 is the same to V1, is the same color as V1 to V1 to VI. Okay, then what we do is disconnect this because we do want a tree. I'm still not convinced if this one is needed or not, but I'm just explaining what I'm doing here. So I disconnect that. I can't see this color. Pink. Do we feel like pink? Yeah, sure. So we disconnect V1, V2, and then like attach V. And let me just color this one the same color as that. So we reattach that one. This one's gone now. And we have a path from V2 to VK, and VK to VI, this the other color. VI connect to V1, V1 connect to VI plus 1. I will argue this is here like when it wasn't a a union of two monochromatic path, but I don't think it is necessary in this case because yeah, we assume PI is one of the two already. So this is like a restore of order when these two color like, yeah, I don't think this is necessary, but when they are the same color as that, so when they are color 2, let me just color them. Okay, from end to the front, then attach VI plus 1 to the front. This is when VI plus CVI VI plus 1 equal to 1 V1 VI. So let's see, I'm just copy this down again. So we have VI plus 1 equal to this one here. I'm just gonna draw it. And there will be color 1. I'll just draw color 1 to start with. Okay, again, you don't want a cycle, so you disconnect that one. This one's gone. Your paths go from VI plus 1 to VI, which is here, to V1, and come back here as a single path. But these two, I'm not convinced they are needed, given I think these three captured all the cases. I don't know what I was thinking. Anyway, and then we go on to the next iteration because it's like construction, right? So we set I equals to I plus 1, increment I by 1, relabel the vertices in the order of 1 to I. So instead of having like I plus 1 at the start, it will be confusing for the next iteration. So we just relabel them, like rename them, be like 1, 2, 3 until I plus 1, but also like I equals to I plus 1. We have incremented I, so this is in fact the new I. Maybe I should have used I dash for math notation. I used that for CS notation, but anyway. And we run the algorithm again because PI is either union of two or monochromatic. Run the algorithm again. I have showed that the property of PI has been preserved, which is what we are proving. Okay, so we know we can get a path through everything. So a Hamiltonian path, not necessarily a Hamiltonian cycle. We know that like when we exhaust new vertices to choose from, that is when Kn excludes Pi vertices is empty. So I guess Vkn exclude Vpi is empty. That means that Pi included all the vertices, and we have a Hamiltonian path from V1 to Vn covering all Kn. Now we just need to connect the last bit to see if the property still holds, and if we connect V1 to Vn, and yeah, And if the property still holds, then we will have a monochromatic or union of two monochromatic Hamilton cycle, which is what we want. Okay, we connected. For n greater or equal to 3, we have at least one of the following. So I'll construct what we had first. That is my cat. Hello, George. Okay, so we have some path. Let's say it has 2 colors. It may or may not have 2 colors, but just let's say it have 2 colors. And this is from V1 up until Vn. Now we are just connecting V1, Vn, and see what color it is. And discussing all possibilities and see if the property is preserved. Okay, so the first case, V1, Vn is equal to Vn, Vn minus 1. I guess I should label that. That is too sick. Vn minus 1. And this is V2. Let me color that. So the first case is that V1, Vn equals to Vn minus 1. So that is monochromatic union of 2, right? Or if they are exactly the same color, then that would be monochromatic. The property holds. The other case is V1n equals to V1 V2, which means that I'm gonna grab further down here. We have V1 Vn equals to V1 V2, so that is still union of 2, right? Or guaranteed to be union of 2. One of them can be empty. I don't know. The third one is monochromatic Hamiltonian path. I'm gonna copy this and just n minus 1 with the highlighter. So the path itself was monochromatic. All of them is color 1. Then we will have V1, V2 equals to Vn, Vn minus 1, because by the construction we know that if it's monochromatic, then yeah. Okay, but that's okay. So we can pick this to be whichever color. If it's color 1, then the whole Hamiltonian cycle is monochromatic. Or if it's color 2, where's my sign? Yeah, if it's color 2, then that's union of 2 paths, and this is like the only part in the color 2. So we kind of go through case by cases and proved it by construction it iteratively. I hope this makes sense. If not, I can meet up with you next week, but also like I'm busy with stuff. So I guess we will see. Alright, see ya recording.